Picture two clocks. One sits on Earth, the other sits inside a spacecraft, hurtling away from Earth at extreme speed. Both clocks start at exactly the same moment. Both are mechanically identical, perfectly calibrated, built by the same engineers. And yet, according to one of the most rigorously tested principles in the history of science, those two clocks will not agree with each other. Not because one is broken, because time itself is not the same thing for both of them. This isn't a thought experiment confined to chalkboards anymore. It's been measured directly, repeatedly, using atomic clocks flown on airplanes, satellites, and particle accelerators. It is, quite literally, the reason the GPS app on your phone gives you accurate directions instead of placing you several miles off course. Time dilation is real, verified, operational, built into devices you use every single day without thinking about it. And once you take that single fact seriously, something extraordinary falls out of the mathematics. Something that sounds, at first, like it has to be a mistake, or a trick, or science fiction dressed up as physics. Right now, humanity's fastest spacecraft, NASA's Parker Solar Probe, is the fastest object humans have ever built, reaching a recorded speed of 430,000 miles per hour during its closest pass by the Sun in December of 2024. At that speed, you could circle the entire planet Earth in under 4 minutes. You could fly from New York to Tokyo in about a minute and a half. It sounds, by any everyday human standard, absurdly, impossibly fast. And yet, at that same speed, reaching Proxima Centauri, the nearest star system beyond our own, would still take more than 6,000 years. 6,000 years, at the fastest speed our species has ever achieved. For context, that's longer than the entire span of recorded human civilization, longer than written language has existed, longer than the pyramids of Egypt have been standing. So here is the real question, the one this video is actually built around. Given that brutal mismatch between our fastest technology and the staggering size of the universe, how far could a human being actually travel through space within the boundaries of a single human lifetime? The answer is going to surprise you, and not for the reason you might expect. Because hidden inside the very same equations that seem to trap humanity helplessly close to Earth, the equations Albert Einstein published in 1905, is something that sounds almost like a loophole. A correctly understood, mathematically verified, real feature of how the universe actually works that could, in theory, allow a single human lifetime to span not just a few light years, but potentially millions of them. This isn't going to be a video about warp drives or wormholes pulled from science fiction. Everything in this story comes from physics that has already been tested and confirmed. What changes is simply how far you're willing to push it. So let's actually do the math properly and find out just how far a human being could really go. Before we get to the strange part, we need to establish exactly how slow fast really is, by the standards of the cosmos, because most people's intuition about speed is calibrated entirely by things that happen on Earth, and that intuition becomes almost useless once you leave the atmosphere. Let's start with the Parker Solar Probe itself, because it's a genuinely remarkable piece of engineering, and the actual numbers deserve a moment of appreciation before we move past them. Launched in 2018, it spent 6 years using repeated gravity assists from Venus to gradually tighten its orbit around the Sun, getting closer with each pass. On the 24th of December, 2024, it achieved its record-breaking flyby, reaching a velocity of 690,000 kilometers per hour, or about 430,000 miles per hour, relative to the Sunday. In scientific terms, that works out to roughly 0.064% of the speed of light. Let that number sit for a moment, because it's the single most important reference point for everything that follows in this video. 0.064% of light speed, not 6%, not 0.6%, 0.064%. Humanity's fastest achievement to date represents a number so small relative to light speed that on a chart with light speed at the top, our absolute best engineering effort would be a barely visible smudge near the very bottom. Now let's apply that real speed to a real interstellar distance. Proxima Centauri sits about 4.2 light-years from Earth. A light-year, the distance light travels in a single year, works out to about 5.88 trillion miles at Parker Solar Probe's record speed, maintained continuously, which is itself an unrealistic best-case assumption, since the probe isn't actually traveling toward Proxima Centauri and isn't designed to sustain that velocity indefinitely. The journey would take a little over 6,000 years. 6,000 years, at our fastest, to reach the closest star. This is the brutal, sobering reality that any honest conversation about space travel has to start with. Chemical rockets, the kind that have launched every human being who has ever left Earth, including every Apollo astronaut, are nowhere near fast enough to make interstellar travel remotely practical within a human lifetime, using simple, constant velocity, straight-line travel. If this were the whole story, this would be a fairly short, fairly depressing video. Humanity, in this framing, would be permanently and essentially trapped within its own solar system, with even our nearest stellar neighbors functionally unreachable for as long as our species exists. But this isn't the whole story, because there's a piece of physics we haven't introduced yet, and once it enters the picture, the entire calculation changes in a way that almost nobody, outside of physicists and dedicated science communicators, properly understands. In 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that quietly rewrote the relationship between space, time, and motion. Buried within what's now called special relativity is a consequence that sounds, on first hearing, almost too strange to be real. The faster an object moves relative to an observer, the slower time passes for that object, from the observer's point of view, not as an illusion, not as a trick of perception, as an actual, physical, measurable difference in how much time elapses. This is what's called time dilation, and it has been confirmed experimentally so many times, in so many independent ways, that it now sits among the most rigorously tested predictions in the history of physics. Atomic clocks flown on commercial airliners, moving at ordinary aircraft speeds, register a tiny but precisely measurable and predicted time difference compared to identical clocks left on the ground. Muons, unstable subatomic particles created when cosmic rays strike Earth's upper atmosphere, should decay long before reaching the ground at the speeds physics says they're traveling. And yet we detect them at sea level in exactly the numbers predicted, because time dilation effectively extends their measured lifespan from our reference frame. And perhaps most relevant to your everyday life, the GPS satellites orbiting Earth experience time passing slightly differently than clocks on the surface, due to a combination of their orbital speed and the weaker gravity at their altitude, and these tiny relativistic corrections, on the order of fractions of a millionth of a second per day, have to be built directly into the GPS system's software. If engineers ignored them, location errors would accumulate at a rate of several miles per day. Every time your phone correctly tells you which exit to take, you are, quite literally, relying on Einstein having been right. Here's the part that turns this from an interesting footnote in physics into something genuinely mind-bending for interstellar travel. The effect of time dilation is barely noticeable at ordinary speeds, even speeds as fast as the Parker Solar Probe, but it becomes dramatically, explosively significant as an object's speed approaches the speed of light itself. The relationship isn't a straight line. It's a curve that stays almost flat for a very long time, and then rockets upward. At 10% of light speed, the time dilation effect is still fairly modest. At 50% of light speed, it becomes meaningfully noticeable. At 90% of light speed, for every year that passes for a traveler, more than 2 years pass back on Earth. At 99.99% of light speed, a traveler could experience roughly a decade of their own life passing, while back on Earth, everyone they ever knew has aged and died. Possibly an entire generation or two has come and gone. This is not speculation. This is confirmed, tested, mathematically rigorous physics. The only genuinely open question is whether humans could ever build something capable of actually reaching speeds close enough to light to make this effect dramatic enough to matter for real interstellar travel. And that's where the conversation shifts from, is this physics real, to, is this engineering remotely plausible, which are two very different questions with two very different kinds of answers. Let's now do something most popular science content never actually bothers to walk through properly. The real math behind a theoretical, physically grounded interstellar journey, using a specific, well-studied scenario that appears repeatedly in serious physics literature on this topic: constant acceleration at 1g. Here's the setup. Imagine a spacecraft equipped with a propulsion system, hypothetical, beyond anything humans have actually built, but not violating any known law of physics, capable of accelerating continuously at exactly the same rate as Earth's gravity, what physicists call 1g, for the entire outward leg of the journey. This particular acceleration value isn't arbitrary. It's chosen specifically because it would feel, to the people on board, exactly like standing normally on Earth's surface. No crushing g-forces, no floating in zero gravity, just ordinary, comfortable, everyday weight for the entire trip. Under this scenario, a spacecraft would spend roughly the first year accelerating, gradually approaching speeds close to light, then, for journeys to extremely distant destinations, spend a middle portion of the trip cruising at a velocity extremely close to the speed of light, before eventually decelerating at the same 1g rate to arrive at the destination at a survivable, comfortable speed, rather than smashing into it. Multiple independent physics analyses, including peer-reviewed and widely cited calculations published in academic and technical sources, converge on broadly similar figures for this scenario. Reaching Proxima Centauri, 4.2 light-years away, under constant 1g acceleration the entire way, would take the crew aboard the ship somewhere in the range of 2.5 to 3.5 years of their own, personally experienced time. Meanwhile, back on Earth, due to the time dilation effect we just established as real and tested, somewhere around 6 to 7 years would have actually elapsed. Already, this is a genuinely strange and wonderful result. A 6,000-year journey, using our actual current best technology traveling at constant velocity, compresses down to a multi-year journey for the crew, using a hypothetical but physics-compliant 1g constant acceleration engine. But this is just the beginning of how strange this gets, because the effect doesn't scale in a simple, linear way. It compounds. Push the destination further out, and the numbers become almost unbelievable. Under the same constant 1g acceleration scenario, reaching the center of our Milky Way galaxy, a destination roughly 26,000 light-years away, would take a crew member somewhere in the range of 10 to 20 years of their own personal, experienced lifetime, according to figures published in multiple independent physics analyses of this exact scenario. Meanwhile, back on Earth, somewhere between roughly 15,000 and 50,000 years would have passed, depending on the exact assumptions used in the calculation. And if you push even further toward the Andromeda Galaxy, our nearest large galactic neighbor, sitting roughly 2.5 million light-years away, the same 1g constant acceleration scenario suggests a crew member could complete the one-way journey within somewhere between roughly 28 and 58 years of their own personally experienced lifetime. According to different published calculations using slightly different assumptions, back on Earth, millions of years would have passed. The crew member would have aged a single human lifetime. Human civilization back home, if it still existed in any recognizable form at all, would have had millions of years to evolve, transform, or vanish entirely. This is the loophole referenced at the start of this video, and it's worth being extremely precise about what kind of loophole it actually is. It is not a loophole that lets you break the universe's speed limit. The speed of light remains, as far as every confirmed experiment in physics has ever shown, an absolute, unbreakable ceiling. What time dilation offers instead is something almost stranger. A way for a single, finite human lifetime, experienced normally at 1 heartbeat per second, to map onto an almost arbitrarily large amount of cosmic distance and elapsed external time, simply by getting close enough to that speed limit and staying there long enough. At this point, an honest video has to slow down and address the obvious question hanging over everything we just calculated. If the physics genuinely works this way, why haven't we built this spacecraft yet? Why are we still using chemical rockets that top out at a tiny fraction of a percent of light speed? The answer comes down to one brutally unforgiving piece of physics that doesn't get nearly as much popular attention as time dilation, but is, in practical terms, by far the bigger obstacle: energy. Specifically, the staggering, almost absurd amount of energy required to accelerate any object with mass anywhere close to the speed of light. As an object's speed approaches the speed of light, the energy required to add each additional increment of speed increases dramatically, following the same relativistic mathematics responsible for time dilation in the first place. Getting a spacecraft to even 10% of light speed using current or near-future propulsion concepts would require energy reserves vastly beyond anything humanity has ever produced for a single mission. And getting meaningfully closer to light speed, the kind of speed needed to unlock dramatic time dilation, pushes the energy requirements into territory that some physicists half-jokingly describe as requiring converting a significant fraction of a small moon's worth of mass directly into pure energy, just for propulsion. There's a second, related problem that compounds the energy issue even further: fuel mass. A spacecraft using any propulsion system that works by expelling mass to generate thrust, the same basic principle every rocket ever built relies on, faces a brutal mathematical relationship called the rocket equation. To reach extremely high fractions of light speed and then decelerate again at the destination, the amount of fuel required, relative to the mass of the actual payload and crew, becomes so enormous that, according to detailed calculations published by physicists examining exactly this scenario, the required fuel mass for a realistically sized crewed spacecraft attempting a serious relativistic journey can end up vastly exceeding the total mass of the spacecraft itself. often by factors that make the entire concept practically, though not theoretically, impossible using any chemical, nuclear, or even currently theorized advanced propulsion system. This is the genuinely important distinction this video needs to draw clearly, the one that separates solid science communication from science fiction dressed up as fact. Time dilation, as a physical phenomenon, is completely real, fully confirmed, and mathematically well understood. The relativistic rocket equation, describing how much energy and fuel would actually be required to achieve the speeds necessary to meaningfully exploit time dilation for interstellar travel, is also completely real, and it currently describes requirements so far beyond present or even plausible near future human engineering capability that serious physicists generally treat large-scale relativistic interstellar travel as a theoretical curiosity rather than a near-term engineering goal. So, which is it? Is the loophole real, or is this video walking it back at the last minute? The honest answer is that it's both, simultaneously. And that nuance is exactly what makes this story interesting, rather than either purely depressing or purely fantastical. Here's where the deeper, more interesting question emerges, the one worth genuinely sitting with. The physics says one thing very clearly, and the engineering says something else very clearly. And the gap between those two answers represents one of the most fascinating, unresolved frontiers in how humans think about our own cosmic future. On the physics side, there is no known law of nature that forbids a spacecraft from eventually reaching extremely high fractions of light speed, given a sufficiently advanced and sufficiently powerful energy source. Special relativity doesn't put a cap on how close to light speed a massive object can get. It only forbids actually reaching or exceeding light speed itself. In principle, given enough usable energy, applied efficiently enough, over a long enough acceleration period, the 1g constant acceleration scenario described earlier, and the staggering travel time compression it implies, remains entirely consistent with everything physics currently understands about how the universe works. On the engineering side, every concept currently under serious discussion, ranging from nuclear pulse propulsion concepts dating back to projects like Project Orion in the 1950s and 60s, to more modern theoretical concepts involving fusion propulsion, antimatter engines, or even more speculative ideas like the Bussard ramjet, which would theoretically scoop up interstellar hydrogen as fuel while traveling, all face the same fundamental problem in different forms: producing, storing, or efficiently harvesting the truly enormous quantities of usable energy required to push a meaningful amount of mass to relativistic speeds, and to do so reliably enough to support actual human passengers across years of continuous operation remains, by a significant margin, beyond current technological capability and beyond any technology currently in serious development. This is where it's worth being genuinely careful and balanced, because there are two very different, equally legitimate ways serious physicists and engineers think about this gap. Some argue that the gap is so enormous, both in terms of raw energy requirements and in terms of materials science challenges like radiation shielding, propulsion efficiency, and structural integrity at relativistic speeds, that meaningful relativistic interstellar travel may remain permanently outside the reach of any civilization bound to using ordinary matter and energy, regardless of how many centuries of additional technological development occur. Others point out that human technological history is full of capabilities that would have seemed equally, almost identically, absurd to people living just 1 or 2 centuries earlier, and argue that confidently declaring something permanently impossible based on current engineering limitations has a consistently poor track record throughout the history of science and technology. Neither position can currently claim to be definitively scientifically correct, because both rest on predicting what technology might or might not eventually become possible, which is fundamentally a different, far less certain kind of claim than predicting what the verified laws of physics themselves allow. Let's bring this back to something a little more grounded, because there's an important, often overlooked piece of this story that deserves real attention. The journey wouldn't just be fast by the traveler's own clock. It would also, from the traveler's own perspective, look genuinely, dramatically different from ordinary space travel, in ways that go beyond simply arriving sooner. As a hypothetical relativistic spacecraft approached a significant fraction of light speed, the crew would begin experiencing 2 additional, related relativistic effects beyond time dilation itself. The first is called length contraction. From the perspective of the moving spacecraft, the distance to the destination would actually appear to shrink the faster the ship moved, exactly compensating, mathematically, for the time dilation effect, so that the crew's own experience of how far did we actually travel and how long did it take remains fully self-consistent, even though it looks completely different from how the journey appears to an observer back on Earth. The second effect involves the visual appearance of starlight itself. At extremely high fractions of light speed, light from stars ahead of the ship would become dramatically blue-shifted toward higher energy wavelengths, potentially even shifting visible starlight into the dangerous, high-energy range of X-rays, while light from stars behind the ship would become correspondingly red-shifted, an effect that several physics analyses of this exact scenario note would actually create a genuine, serious radiation hazard for any real crew attempting sustained relativistic travel, requiring shielding solutions that current material science doesn't yet have a clear answer for. This is part of why serious physicists examining relativistic interstellar travel rarely treat the energy and fuel problems as the only practical obstacles. Even given some hypothetical future solution to propulsion and energy, the sheer physical environment of sustained, near light-speed travel introduces genuinely new engineering challenges that don't exist at any speed humanity has previously experienced. So let's finally answer the actual question this video opened with, directly and honestly, gathering together everything we've established. How far could a human being actually travel through space within a single human lifetime? Using technology that exists today, the honest, somewhat sobering answer is not very far at all, relative to the scale of the universe. Even humanity's fastest achievement, the Parker Solar Probe's record-breaking 430,000 miles per hour, would require over 6,000 years just to reach the nearest star, making any kind of meaningful interstellar travel using current propulsion technology and simple constant velocity flight essentially impossible within any human lifetime, with no exceptions. But the deeper, more genuinely fascinating answer, the one buried inside Einstein's equations, the one confirmed by atomic clocks, satellite systems, and subatomic particles every single day, is this: there is no fundamental physical law preventing a sufficiently advanced form of propulsion, one capable of sustaining acceleration close to 1g for an extended period, from compressing a journey of thousands, or even millions, of light years, as measured from Earth, down into a span of years, comfortably within a single human lifetime, as experienced by the traveler. The physics of the journey, the time dilation, the energy requirements, the relativistic rocket equation, all of it is real, tested, and mathematically rigorous. The missing piece isn't a gap in our understanding of the laws of nature. It's a gap, currently an enormous one, in our engineering capability to actually harness and apply those laws at the scale required. This means the honest, complete answer to the question in this video's title isn't a single number. It's a fork. Bounded by current technology, a human lifetime can carry you, realistically, perhaps as far as the outer edges of our own solar system, and not meaningfully beyond it, bounded only by the actual laws of physics. Assuming some hypothetical future civilization eventually solves the staggering energy and engineering challenges involved, a single human lifetime could, in principle, carry a traveler not just to the nearest star, but potentially across the entire breadth of the observable universe, while a near eternity passes for everyone and everything left behind. There's one final piece of the story worth sitting with, because it reframes the entire question in a way that goes beyond pure physics into something closer to philosophy. If a future human being ever did make a journey like this, accelerating at a comfortable 1g, toward some impossibly distant destination, experiencing a normal human lifespan of activity, growth, and aging aboard the ship, while tens of thousands or millions of years passed back on the world they left behind, what would they actually be doing in the deepest sense? They wouldn't simply be traveling through space. They would be traveling irreversibly into the deep future of everyone and everything they ever knew. There would be no return to the world they left, not because the ship couldn't turn around, but because that world, as they knew it, given enough elapsed time, would almost certainly no longer exist in any recognizable form. The civilization, the language, the descendants of everyone they loved, the very culture they were raised in, all of it would have had the same staggering span of time to change, evolve, or vanish that separates us today from the construction of the first cities, multiplied many times over. This is the genuinely strange, often underappreciated price tag attached to the loophole this entire video has been building toward. Time dilation doesn't just offer a way to travel impossibly far within a single lifetime. It offers a one-way ticket into a future so distant that coming home stops being a meaningful concept altogether. So here's the question worth sitting with as this video closes. If the laws of physics genuinely allow a single human being to outlive everyone they have ever known, not by dying and being forgotten, but by simply moving fast enough through space that time itself leaves everyone else behind, would you take that journey if it ever truly became possible? Would reaching the literal edge of what a human lifetime could ever achieve be worth becoming a stranger to the entire future of your own species?